so this A is SUN gauge field. And this F is the field strength. So, yeah. Yeah. And basically, so we want to understand the feature of this path integral because this explains, for example, so strong force. So over our standard model. And within our standard model, so this, so strong force sector is one of the most non-perturbative sectors that is difficult to understand. And our idea is to understand this force part of strong force. And basically, so looking at the first part is just given by E squared minus B squared. So this is, so basically Maxwell term in the case of abelian theory. And interesting feature of this 4D muse is what is called color confinement. So basically, this is just explaining the color magnetic, so theory of color and color electromagnetic field. And so interesting question about this problem is what happens if we put a test quark, so Q and Q. So. And in the case of Maxwell, it just emits Coulomb electric field, and it just it. But in this case of SUN Yamil theory, what is happening is so color electric flux. Yeah. Form a flux tube.
Yeah, is it important to take this Q the box as a test for particles, or it's okay to be dynamic to add it to the?
So here, so I'm assuming that this is just a test particle because I'm eventually going to talk about one form symmetry, and when this quark is dynamical, that part becomes subtle. So here I'm assuming that this is really just a test particle. And so as a phenomenological observation, if we really put just quark and anti-test quark in this Yamil theory, and if we observe how color electric profile is formed, this flux tube is formed, then interparticle potential of this theory is proportional to the distance. This is the distance, relative distance. So it's proportional to the distance. So that means that force that fills this test particle is given by this derivative. And this is independent of interparticle distance. That means that even how this test quark is separated from anti-test quark, this test quark is constantly attracted to this anti-quark, even however they are far away separated. And because of this constant force, constant attract force, this color electric object is should form a color singlet object by forming a pair of quark and anti-quark. And this is why we cannot observe single quark in our universe. So everything what we observe is forming a color singlet hadron like meson or baryons. So here, so I just explained that so this color electric flux form a flux tubes, but why or how this flux tube formation occurs. And this is a very difficult dynamical question that, that is difficult to be addressed if we try to analytically study this for the Yamil theory. But there are several scenarios that explaining, and one of the famous scenarios that explain this flux tube formation is a dual superconductor picture. Developed by, say, Nambu, Toft, Polyakov, Mandelstam, many people developed this idea. And the idea is so, yeah, so in the usual superconductor case, so what is happening is inside that superconducting matter, so electric charge is, so electric charge is condensed in vacuum. So everywhere inside the vacuum, there is some electric charge. Then if we put test magnetic charge, so test magnetic charge, and let's put anti-magnetic charge. Then because of Meissner effect, so B field has B flux tube is formed. And this is what we understand from the theory of superconductivity or BCS superconductivity. And in the case of BCS superconductivity, this electric charge condensation occurs by Cooper pairing. And idea of this dual superconductivity is taking electric and magnetic duality of this picture, because Maxwell theory seems to be invariant under exchange of electric and magnetic fields. So let's just take that electromagnetic dual of this picture. Then, so this electric charge condensation is replaced by some magnetic charge condensation. So here I'm not talk. Yeah, here I'm not specifying what is the charge of this electric charge. So yeah, so here, yeah. So let's just say that this is some bosonic particle having electric charge, but this can be charged two charges. And so whatever electric charge, anyway, here I'm assuming that electric charged one field is condensing. Yeah. But yeah, so in the actual world, because Cooper pair is condensing, so what is condensing is electric charge two object. Yeah. But in this explanation, that charge is so value of charge itself is not so important. So let me not talk about that part. Yeah. So taking just electromagnetic dual of this electric charge condensation, then magnetic charge condensed object appears, then so if we, and this test magnetic particle is replaced by this test electric particle, and so E flux tube is formed. And this picture is quite analogous to this picture. So if this happens for the case of SUN gauge theory, then this color charge test particle is confined because of this flux tube formation. If that color magnetic charged object is filling the vacuum everywhere. So that is the idea of dual superconducting picture. So some color magnetic. Yeah. And so, but at this moment, this is just a scenario that explains color confinement. So how can we test this one?
On the left side of that picture, why is the condensation crucial for this amount?
This magnetic flux tube?
Yes.
Yeah. That part I have to write down Maxwell equation. But basically, since electric field is everywhere, so basically, so if this magnetic field is emitted, nothing can screen this B field. So B field itself, so B magnetic flux itself should be conserved. But if electric field condensation is everywhere, so basically, yeah. So yeah. Yeah, let me. Yeah, so for example, so if we write down effective theory, then so it becomes yeah. Let's say this one bottle potential. So so this is one of the good effective theory describing this condensation. And this phi is a field that describes a low energy limit of this electric charge condensation. And so when this has a non-zero wave, then and let's for simplicity, let's take B is sufficiently large. Then in this case, so this phi can be parameterized by e to the I times phi over f. So this is just a phase. Then this part basically says, so this becomes b squared.
It's not from that theory that works.
Yeah.
Condensation of this electrically charged plant. I mean, of course, in order to give a BEV, you gotta have something.
Right.
The usual Higgs mechanism, right? Particle physics, you don't really require that.
But because of Higgs thing, so this magnetic field gets mass. So, but the B field itself should be preserved. So B magnetic flux should be preserved. So electric field basically field strength wants to be zero as much as possible because of the Higgs mechanism. Otherwise, because gauge field obtains a mass gap. So if that field itself is surviving everywhere, then that requires too much action density. So violation of this non-zero magnetic field sector should be as much as wants to be as small as possible. Then so this violation of non-zero magnetic field region should want to be minimal, and that is a flux tube. Yeah. Right. So yeah, in order to make complete, so basically looking at this with B squared is much very large quantity. Then gauge field wants to, so this wants to be zero as much as possible. Then this tells us so F mu nu wants to be zero. But since magnetic monopole is only present here and here, so magnetic field surrounding this two sphere should be magnetic charge everywhere. So this condition and this condition does not fit together. Or so somewhere inside this sphere, so there should be non-zero magnetic field region. So this violation of this condition wants to be small, as small as possible, and this forms a fracture. Yeah, yeah. So basically, even if you take that limit, so yeah, so that large B limit is taken just for simplicity, and basic physics is the same, even if we consider that case. Yeah. Okay. But this monopole is a test monopole, so yeah, yeah. Yeah, of course, yeah. So this mass of monopole becomes larger and larger in that limit, but it's test monopole here. Yeah, so far, so I just give one of the picture that explains confinement. But so how we want to test this dual superconductor picture? And in order for this purpose, this yeah, this theta term turns out to be quite helpful to understand the validity of this dual superconductor picture, or what kind of prediction can we obtain from that dual superconductor picture. And so in order to see the role of theta angle, so let me explain several properties. So one of the feature is theta is a 2-pi periodic quantity. And I want to explain this both from Lagrangian viewpoint and Hamiltonian viewpoint. And so from Lagrangian viewpoint, so partition function is given by this formula, but so we can say that so this quantity and this integrand of this turns out to be, strictly speaking, it's not total derivative, but almost total derivative. And because of this feature, so this is quantized to integer. So this is so, and this quantity is called instanton number. And because of that, so that partition function as a function of theta can be expanded in terms of instanton number such that it gives ei theta n times n. And since theta angle appears only here, and this n is quantized to integer, so this suggests us so that theta plus 2 pi turns out to be same with z of theta. So this parameter in front of the coupling of E dot B term is has some mysterious periodic property, and which is evident in this Lagrangian viewpoint. But if we try to see this from Hamiltonian viewpoint, this is a bit mysterious. And in order to go from this Lagrangian formalism to Hamiltonian formalism, let me temporarily write everything in Minkowski with A0 equal 0 gauge. So then it becomes So this is a Lagrangian in temporal gauge in Minkowski. So in Euclidean, I is not here and I is here. So there is a relative I in front of theta. But in Minkowski, you get I in both cases. So you do not have relative I in front. That's technical. That's just the technical stuff. But from this one, so we have to obtain conjugate momenta.
You have a subscript and should say it's Minkowski version.
Yeah. So you're right. Yes, yes. So in Hamiltonian formalism or operator formalism, we have to get a pair of field and conjugate momentum field. So we want to get it. That's and we obtain, yeah, square plus yeah, you get this formula. And what we usually call the electric field is this quantity. And in usual case or theory without theta term, this electric field and conjugate momentum gauge field are parallel. So there is no subtlety. But in the case of theta, you get extra term here. And this is causing the Witt effect. That is, so if we look at electric field, we get d squared. Right. So yeah, so it's basically I just rewrite this one. So this is basically. So if we try to, so let's assume that we are having some particle and try to measure electric field for that quantity, then this one, so this pi goes to 1 over r. So this operator becomes a derivative operator of gauge field. And since gauge field has some periodic quantity, is a certain periodic quantity. So if we try to measure the charge, then this part gives a quantized electric charge. But this part basically gives a fractional shift. Proportional to magnetic charge. And this is nothing but a Witt effect. Yeah. And yeah, and if we write down the Hamiltonian, so Hamiltonian, then yeah, if you just write down this, if you obtain it by this Legendre transformation, what you would get is you obtain this quantity. And you may encounter some mysterious thing. So here I said theta is a 2 pi periodic parameter. But if you look at this formula, obviously h theta plus 2 pi is not h of theta. So then what about this 2-pi periodicity? And so actual statement of this 2-pi periodicity of theta is saying that so physics at theta and theta plus 2-pi are unitary equivalent. And so actual statement is, so this h theta plus 2-pi should be given by some unitary operator that relates theta plus 2-pi and theta. And this u is given by yeah, for some reasoning that I do not explain here, so this coefficient in front of this Chern-Simons form has to be integer. So otherwise, this operator is not SUN gauge invariant. And if you sandwich this conjugate momenta with this u, it turns out that theta is shifted by 2-pi, and you obtain everything is consistent. Large A. Sorry. Yeah. Thank you so much. Yeah. So sorry. This is only space constant time region. Yeah. Yeah, since I'm working on Hamilton formalism, time direction is special, so this is integrated over 3 space. Yeah, right. And so especially so because of this unitary equivalence, so states itself do not have to be periodic in theta, naively on the nose. And actually, this is happening for the case of a vacuum in the case of confinement state. And so yeah, right.
Can you say elaborate a little bit more what is by state deniability should be?
Yeah. So here I write down explicit example here. So yeah, right. So yeah. So right. So this vertical axis is energy. And let's write down the energy as a function of theta, for example, for this confinement vacuum. And if we believe this dual superconducting picture, so we say that confinement occurs if magnetic charge is condensing. So let's assume that here, so EM equal 0, 1 condensation occurs. And so it turns out, yeah, so here I have to give some more argument, but it turns out that this is this kind of quadratic form in terms of theta, because basically if we introduce theta angle, this Witten effect says that this neutral electric charge starts to acquire fractional electric charge, then because of that Coulomb force, Coulomb energy of this condensing particle, that ground state energy is increasing as a function of theta. And this electric charge does never come back to 0 because it's just linearly depend on theta, so it's just increasing the energy. So this state is not 2-pi. not 2π periodic. So what is happening? And so you next, then you can consider EM equal -1 condensed state. So this kind of quantity is called dione because it has both electric and magnetic charge. Then if we turn on theta, so this EM, so it's somewhere here, so this EM becomes, say, theta over 2π 1 according to this formula. Then, so say around here, this EM becomes -1 plus theta over 2π 1 quantity. So magnitude of electric charge is becoming smaller and smaller. So this decreasing energy and something like this. And so this is theta equal 0. And this point is theta equal 2π. So in order to have a total 2π periodicity of the ground state, single confinement vacuum is not enough to be considered because that one is just increasing the energy as a function of theta eternally. And in order to get good 2π periodicity, you have to consider some other condensed object called dione that has both electric and magnetic charge. Then, as a function of theta, this electric charge is becoming smaller and smaller by summing up this quantized electric charge and fractional electric charge. And you have having the level crossing at theta equal pi.
Another way of saying it is that by getting a distinct 2π periodic in data, you have to include another condensation.
Yes.
Condensation. Otherwise, you will not satisfy the criteria. Is that?
Yeah, exactly. Right.
Yeah, I have a small question. Embarrassingly, don't know the answer to it. But one way of phrasing this is that there are two different STP states, and there cannot be 2π periodic. That's one of it.
Right. That's right.
Pi n periodicity. You could say that states are still 2π. In the large n, it doesn't appear that that's the case. It's just quadratic.
Yes.
Whereas in the R3 process 1 that you studied a lot, they are really 2π n periodic.
They are 2π n periodic.
Are they 2π n periodic in Fourier bills, do you think? I mean, there's no reason for them not to be. But in the large n, we may never see them. Yeah, but in large n, that 2π n itself goes to infinity, so that's different. I phrase everything, it seems that they will never be periodic because it's linearly growing. Right. So in this abelianized picture, that 2π n periodicity cannot be seen because we integrate out all W boson secretly in this picture. So that periodicity. I see. So you're thinking. Yeah. But I believe no one really knows the answer to that question. Yeah. The other hand, the Lagrange formulation, didn't you need the non-ideal nature of the J theory, the RPY that is 2π periodic? Yeah, that's true. That's also true. Yeah. But this 2π periodicity itself is more robust because basically just you are having a Chern-Simons form that shift theta by theta plus 2π. So this is basically general feature, even if we assume abelianization of dynamics by, for example, secretly adding Higgs field or something. Yeah. Just a phrase, make another comment. You see, 2π n periodicity is also non-trivial from this point of view. You still have to unitarily transform. That's true. Yeah. This being non-trivial although there's no strong argument that they really.
Yeah, I completely agree with you. Yeah. Okay, yeah, right. And that is real. Yeah. Yeah, that's quite not trivial. Okay. Yeah.
Why the 2 pi n theory? I think I just.
For that purpose, I have to explain GN1 form symmetry, and that is really the next topic. So let me move. Yeah. 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 Right. Yeah. So here, yeah. So here, this argument, yeah, first, what we have seen is assuming dual superconductor picture, we can predict this kind of non-trivial phase transition at theta equal pi. And in order to make theory to be 2 pi periodic in this sense, so if you assume monopole condensed vacuum, then you also have to have dione condensed vacuum, and there should be a level crossing between them as you change theta angle. But so this picture, so this phase, for example, phase transition at theta equal pi is predicted from here from dual superconductor picture. But this is just one of the scenario of confinement. So it's a natural question that can we have more robust argument to claim the physics at theta equal pi has to be, for example, spontaneous CP breaking has to occur at theta equal pi, something like that. And this turns out to be possible by using the recent development of symmetry, and that is the next topic. So yeah, so yeah.
One basic question.
Yes, please.
Yes. So yes, my understanding was that therefore 2 pi period suggests that confined vacuum cannot consist only of confinement of 0.1. You must include minus 1.1.
Yeah.
Is this inclusion of a minus 1.1 diode is sufficient to fully restore 2 pi periodicity, or you have to iterate this?
No, you have to iterate it. Yeah, exactly. Yeah. For example, yeah. Okay. Yeah, for example, yeah, exactly. Yeah, that's really, yeah, thank you for pointing it out. Yeah, so so for example, let's say this is minus 2 pi. Just with minus 1 dione and 0, 1 monopole, you cannot have ground state at theta equal 2 pi. Then you want to have another branch, something like this. Then this quantity turns out to be 1, 1 dione. And this basically continues. So say if you are having 4 pi, then you want to have this branch. This goes something like this. Yeah, something like this. And this turns out to be minus 2, 1, etc., etc.
Lattice of test components.
So entire charge lattice of electromagnetic charges are necessary to fully have 2 pi periodicity of theta, at least in this abelianized regime. Yeah. Okay. Yeah. And so let me give more robust explanation of this phenomenon, since I think you now get a good physics motivation to understand it, and here I'm going to explain about symmetry here. And since this is the first talk of this conference, I will also want to be pedagogical about this generalized symmetry. So first, let me begin with the conventional view of symmetry. So yeah, this part is very quick. So if we are having some Lagrangian, and if this Lagrangian is invariant under phi, so this has some invariance in for some continuous transformation like U1 phase rotation, then we get a net current. And that satisfies del mu J mu equals 0 as on-shell equation. And while this is a classical statement at this moment, but basically Ward-Takahashi identity says this is also true in quantum version. So even in quantized version. If you look at this kind of operator, or 1x1. If you consider this kind of correlation function, then if you take derivative for x, then this turns out to be 1 q. Away. Yeah. Yeah, something like this. So basically this says as long as this x is separated from other insertion of local operator, this naive classical conservation law is okay. And if this hits to other local operator, then that local operator is transformed by this symmetry transformation. This is so this is Ward-Takahashi identity. Yeah. So this is the conventional view of symmetry in the context of quantum field theory. And it's important that although we consider just global symmetry, out of global symmetry, we obtain some current that conserves locally. And because of this local conservation, for example, so you can do a lot of operations such as introduction. So. Oh. And for example, this allows us to introduce, for example, background gauge field. Yeah. Yeah, something like this. And because of this conservation law, even if basically shift A by total derivative plus something, then by integration by part of this derivative, this acts on del mu J mu, and because of this conservation, so basically, yeah, almost, yeah, so you can basically almost ensure the invariance of this partition function under the background gauge transformation. Sometimes this is broken and this is important for anomaly, but basically, so you can ensure the background gauge invariance for thanks to this local form. And in modern view of symmetry, so basically you want to generalize the notion of symmetry that has the merit of this kind of good property of symmetry as much as possible. And this idea gives a generalized symmetry. And the generalized symmetry basically says that so is basically equivalent to the say, data of topological operators where this meaning of topological is basically equivalent to the conservation law. So local. Yep. And let me explain what this actually means. So here, so we just looked at that. So if we are having this local form of the conservation law by current operator, then you can obtain this kind of Ward-Takahashi identity. And let me rewrite that. So using Neta charge, not current. So for this purpose, so let me rewrite. Let me define Q of sigma. Sigma is a some d minus 1 dimensional submanifold in space-time. And let me just integrate this. Surface form. So basically, we just integrate this Neta current on just the surface. So typical example is so if we are having time and space, and if we just sigma as a constant time slice, then Q of sigma is really the usual Neta charge. And in this case, ds0 is really the dx1, dx, d minus. Yep. Then basically, yeah, if you define this Neta charge, then starting from Ward-Takahashi identity, if you compute this kind of operator, so this correlation function, including this Neta charge, turns out to be independent of a small deformation of sigma. And basically, so if you are starting from this current form of Ward-Takahashi identity, you can derive this property. And it turns out that you can also derive inverse property. So if this quantity is basically independent of any small deformation of sigma for any choice of sigma, then you can also derive that you can also derive this formula for the Ward-Takahashi identity. And this independence of small deformation, basically, so we just call that Q of sigma is topological. So criterion of basically this topological operator is basically just an integrated version of Noether charge. And accumulating all the data of this basically Noether charge, this should be nothing but a symmetry of quantum field theory. So basically we call this set of or data of topological operator as a symmetry or generalized symmetry in quantum field theory.
Clarify. In the case of continuous symmetry, right? It's very explicitly why follows the nature of operators, the 1, 2, and 2, the independence of different under the small difference.
Yes.
For discrete symmetry, if I'm given a question about that,
Mm-hmm.
would you take what you just did this argument as a justification why this is a good definition of symmetry? In that, if you assume Q is a invariant under small deformation, then you can get the associated the global version of the word Takahashi identity.
Right.
Reasoning why that also applies to the discrete symmetry.
Exactly. Okay. Yes. Yeah, for already 1 hour has passed. So okay. Yeah.
I spend 50 minutes.
Okay. Yeah. So yeah. And before going to Yamil theory, so I also want to talk about that discrete case, for example, Ising model example. Here I'm just having classical Ising model. And classical Ising model basically says so you are having the lattice and say at point you are having a spin that takes plus or that takes +1 or -1. So it's just describing a spin up or spin down case. And classical Hamiltonian is basically nearest neighbor coupling of beta. Yep, something like this. And the partition function. Partition function is summing up all spin set of all spins that have. And looking at this formula, it's obvious that we are having this symmetry. Let's say spin at site x is mapped to minus spin x. So up spin goes to down spin. Then since Hamiltonian is quadratic in S, so under this global operation, this is invariant. But here, so I'm just saying that symmetry in quantum field theory is related to topological operator. So you can think of, so what is topological operator? So this is a symmetry. And the answer turns out to be very simple, but while it's a bit non-trivial. So basically idea is so what is the counterpart of this nether charge in this G2 symmetry case? And answer turns out to be you just draw this kind of line or d minus one dimensional surface. And for this bond that describe hopping from x to x prime, this beta is flipped to minus beta. So yeah, so that means E of, yeah. So let me denote this is sigma and U of sigma with some insertion of other local operator turns out to be described by this S of x, E of, yeah. With this beta x prime is plus beta minus plus beta if this x prime does not go through. Yeah, so for example, this link does not go through this yellow surface. So this one is giving just plus beta. But if x prime goes through across sigma, then this beta has to flip its sign. Yeah. And let me check whether, let me check several property first. Let me first check this U sigma is topological. Yeah. So here we are having this yellow line. And in order to see its topologicalness, so let me pay attention to this spin. And since this spin is just a dummy variable in this path integral, so you can define S prime x given by minus S of x. And under this change of variable, so this spin is not flipped while this spin is flipped. So for this one, originally you are having minus beta coupling, but since you get extra minus sign, this minus becomes plus. So this yellow line goes away, right? And the same is true for this one. So this spin is not flipped while this spin is flipped. So you get extra minus sign. So originally this was minus beta, but you get plus beta. So this one also goes away. But let me next pay attention to this one. Originally this was plus beta coupling, but again, you get extra minus sign. So this plus beta goes to minus beta. So now this yellow line should go this way. And the same is true for this one. Then your yellow line goes to this way. So originally you are having yellow line, something like this. But changing this spin variable by this symmetry operation, this yellow surface is moved. But since this is just a change of variable, so if U of sigma, so originally this is sigma and say this is sigma prime. So since this is just a change of variable, you just get this one as long as O1 ON does not contain this this spin variable. Yep. So U of sigma is topological. And for example, if U sigma contains that spin X, while O1, ON, that again does not contain this spin, then under this dummy variable change, now since this dummy variable itself is contained in here, so you get minus X. So this is a count. Oh, I already erased Ward-Takahashi identity, but this is a counterpart of the local term appearing on the right-hand side of the Ward-Takahashi identity. So this spin variable is G2 transformed. If this surface change goes across that spin, yeah. So this really deserves to be called a G2 symmetry generator. Yes, sure. Right.
All these cases, like minimal changes of
Yeah. Please understand that way. Yeah. Actually, so yeah, right. Yeah. Or here, what I mean by small is so deformation. Yeah. Does not go across other operator. So if this surface and these local operators are a bit separated, then under sufficiently small deformation, so it does not touch other operators. So in that sense, I'm calling that deformation is small. Yeah. That is the definition of this smallness. And yeah, so basically, so this condition basically says that deformation is small. So small deformation. Of sigma. Yeah.
These do similar analogous to that with something like scalar pi-4 theory.
Yeah, also in continuous scalar 5-4 theory, yeah, we can do basically similar thing. So, yeah. But in that case, yeah, so basically, yeah, you separate your space-time into some surface. And yeah, here, so yeah, you basically said phi, yeah. Phi x plus epsilon equal minus phi x minus epsilon, where this x is on this surface. So basically, you put a non-trivial twisted boundary condition across this surface that is related by G2 symmetry. Then you can consider the generator.
On the lattice, I guess, takes the sign of the pocket.
Right. Yeah, on the lattice, it's almost same with Ising. Yeah, it's almost same with Ising. Yeah.
I have in the right side, the upper.
Okay, this one.
The second the formula, if the sigma and sigma prime crosses in Sx, then that should be retained by Sx in left hand side and minus X in right hand side.
This one? Other one. This one? Yeah. So correct operation. This Sx becomes S prime X, but this should be minus Sx. That's what I mean here. Yeah. Yeah, so since it's a dummy variable, so you can just rewrite arbitrarily. As you like. So I'm using that degree of freedom of this expression to obtain this form. Yeah. Yeah. And so another perspective is so if you write so let me just rewrite beta xx prime is just given by this way. Then so Hamiltonian becomes x prime beta sx e to the prime. Yeah, so here I'm just rewriting trivial way. But this Hamiltonian has local実 gauge redundancy. Say S of x changes to e of I by, let's say, lambda x, where lambda x takes 0 or 1. And x prime changes to x plus something like this. Then under this operation, so this turns out to be just same. So in this sense, so yes, so this one turns out to be background gauge field for G2 symmetry. So here, so what I have done is just introducing U of sigma and introduction of yeah, introduction of U of introduction of U of sigma is just making beta to be hopping beta to be locally plus beta or minus beta, and just writing that sign as a form of field, it turns out to be a background gauge field. So important lesson we can learn from here is so say network of symmetry generator. Turns out to be you can identify it as a background gauge field. For discrete. Yeah, and I believe this fact appears repeatedly during this workshop, so it's good to make a remark on this fact. Yeah. Okay, so then let me go back to pure for the Yamil theory. Oh.
I think this in the interest of discussion. If you have next neighbor terms, right? Appears to me that gauging medical skills is something have you thought about this?
But even if you have next nearest coupling, so basically, yeah.
Let's say that you have 10 lattice sites away, you have to choose a path. Basically, as well, and a Wilson is.
Right, but since here background gauge field for discrete symmetry is assumed to be flat, so any local deformation is of Wilson loop is okay. So I think it eventually becomes same. Yeah. Yeah. And so since we are now armed with a knowledge of symmetry and its background gauge field, so let me go back to our problem of 4D Yamil theory. And here, so it turns out that we get to have G and one form symmetry. And first, I have to explain what this really means. And yeah. And since I explained the case of Ising model using the lattice discretization, so I think it's good to start with the Wilson's lattice formulation. So and in lattice discretization of Wilson formulation, so it's difficult to draw 4D lattice, so please just imagine everything with 2D. So in the case of Ising model, so degree of freedom is living on spin. But here, so fundamental degree of freedom of Yamuse is given by gauge field. It is having the vector index. So if you leave just degree of freedom on this side, it does not have information of the direction. So natural location of degree of freedom living for Yamuse is on the link or bond variable. And you can just set mu x, which corresponds to mu. Yeah. And it's good that you exponentiate. It turns out that it's good to exponentiate this gauge field on exponential, and let me write that variable as u mu x. And and you can write down. And the lattice discretization of the path integral can be formally written this way, where action can be given by minus. And the meaning of this one is called, so having x here, so we first goes this way to x plus mu hat. Mu hat is mu hat is a unit vector along mu direction. So. And so first you move x to x plus mu hat by this bond link variable, and you now go to x plus mu hat in this way, and go back to form a loop.
So the definition of that link vector,
yeah.
Do you really mean a mu integrate ds is where s is just a scalar parameter?
Yes.
So how come exponent has vector quantity rather than scalar quantity?
Because here I'm having vector index. Yeah.
So exponent can be scalar now. To that extent, then you have almost some of vector scalar.
So it's so here I just pick a component of vector.
Oh, single component.
Yeah, single component. Yeah. So yeah, right. Yeah. And it turns out that this quantity is almost f mu nu of x. So it turns out to be almost a field strength, and so this is a lattice discretized version of the Yang-Mills theory. And this actually has a local SUN invariance. Yeah. So having this one, so basically expanding it as E1 plus I F mu nu plus F mu nu squared minus. And this part is a constant, but this part, it disappeared because of reality, so this part is dropped. So you take trace part of this one, so first non-trivial term is actually higher order term. After taking a continuum limit, that's just an irrelevant operator in the normalization group. So we believe that it doesn't affect continuum limit. Yeah, right. Yeah, exactly. Yeah. Yeah, so it's just, here we just take one of lattice discretization, while there are many variants of discretization. So this SU mu is invariant, and U mu x goes to So this is a SUN gauge transformation parameter at site x, and this is at site x plus mu hat, and it turns out that everything is invariant. So this is having this turns out to be the gauge theory in this sense. And having explained this lattice discretization, it turns out that we can construct GN codimension to topological defect. Which is what we mean by GN1 form symmetry generator. as a very explicit form. Yeah. Yeah. And in the case of Ising model, the way we construct topological defect is flipping the sign of the hopping term. And we really do, yeah, so let me write this as beta. So what we really do is something like this. So we make beta to beta x mu nu. So beta is now becoming a local variable in the sense that e to the r 2 pi over n. So beta is rotated by Gn phase, which is the center of SUN. So yeah. And for example, for this yellow one, this Bx mu nu can be 1, but for everywhere else, this turns out to be just 0. Yeah, something like this. And if we have, for example, yeah, it's difficult to draw again. It's difficult to draw 4D spacetime. So let me just write just 3D. And this yellow line is just a line that penetrates this bracket. And for example, for this bracket, and just pay attention to this link variable u mu x, and change this u mu x by e to the 2 pi I over n u mu x. And importantly, even after this transformation, since this Gn is inside SUN, so this quantity is still living in SUN. And under this operation, then since other bracket is not changed at all, other links on this bracket is not changed at all, so this yellow line now should go away because this is this bracket beta is changed by Gn phase, but it's now absorbed by this Gn transformation. But then, so other bracket, like for this one. For other bracket that is attached to this link variable, so originally beta is just plus beta, but that beta is now rotated by Gn phase, so this one is now changed, changed something like this. Yeah. Yeah, something like this. And so this codimension to a surface related to this Bx mu nu is shifted like this way. So this codimension to is deformed. For change for this specific link variable. So in this way, so you can identify that SUN Yang-Mills theory have Gn one form symmetry.
Let's make a connection to previous ice modeling. So this shift in the use of mu is like change a variable as you did for the spin variable.
Exactly.
and then just reinterpreting what that means in terms of the beta. What has happened to the beta?
Yes.
So you find out that it has to be deformed according to the view contour.
Yeah, exactly. Right. So since it's higher dimensional, it's a bit difficult to imagine, but what we are doing is exactly parallel to for the case of Ising. Yeah, yeah. Right. And let's see. Yeah. And yeah. And we can introduce important observable called Wilson loop, which is given by in continuum, it's just this quantity. And in the case of lattice, so you so in the case of lattice, so if you are having loop inside space-time, then you basically cut this to x mu direction. Then yeah, you basically multiply u mu x along this ordering of this contour. And to make everything gauge invariant, in the case of non-abelian gauge theory, you have to take trace of it. Then everything turns out to be gauge invariant. And this Wilson loop is a charged object for GN1 form symmetry. And which can be, again, understood this way. So let me call this is C, and this is yeah, sigma. So this is a topological defect. And let me try to compute this defect times Wilson loop expectation value. But then, so yeah, then yeah. So basically, so by just changing, yeah, it's difficult to draw. So by just looking at this bracket and changing this U to be this kind of again GN transformation, then this yellow line is now moved like this way. And basically repeating this kind of process, then again now moving this way, then this yellow line is further deformed like this. Then at some moment, this link turns out to be becoming a link shared by this Wilson loop. Then when changing this variable, this goes to, so this yellow lines goes outside of the link Wilson loop. But since this, so one of the link variable inside this Wilson loop is now changed under this redefinition of the variable. So it is changed to be e to the 2 pi I over n times Wilson loop. So when this topological surface and Wilson loop are linked together, then in order to unlink this topological defect, then this Wilson loop has to be changed by this GN transformation. So basically, so it measures the charge of the Wilson loop in modulo n. So And this can be understood more physically, so physical interpretation. So in SUN gauge theory, so particle wants to be labeled by color charge. But the color charge is nothing but a representation of SUN. And it is described by some kind of Young tableau, something like this. Yeah. Yeah, this one. But so SUN gauge theory itself has a code containing a dynamical particle. So gauge field itself is a dynamical particle called gluon. And this is, and gluon is in adjoint representation. And in Young tableau, it's something like this. So n-1 vertical box and one box, etc. So in total, it contains n box. And so let's assume that we put, say, test quark, say, in representation R. And let's put anti-quark in representation R bar. And in the case of pure Maxwell theory, we can just measure charge of this test particle on the node. So you can just the charge of this, for example, test electron by its integer. But in the case of non-abelian gauge theory, so there is a process that since this dynamical gluon itself has this color charge, so if you say, if you are having the soft glue, some gluon exchange, this representation now change to representation times, for example, by adjoint representation. So you cannot, so if you are having a good symmetry that characterizing the charge of this test particle, so this attachment of adjoint representation should not be seen. Otherwise, since this is a dynamical process, so if you could measure the charge of representation itself, that is obviously in contradiction. So what measures GN1 form symmetry is measuring the number of boxes for R in modulo n. Since adjoint representation itself has n boxes, so if you measure number of boxes of representation itself, that's in contradiction. But if you just measure them in modulo n, that attachment of adjoint representation cannot be seen since that is modulo n equals 0 part. So measuring R mod n could be a good conserved quantity for SUN Yang-Mills theory. And this GN1 form symmetry realizing this idea completely. And so this GN1 form symmetry turned out to be quite useful tool to understand the mysterious property of theta periodicity in confinement vacuum. So, 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 so the mysterious property, so let me remind what was the mysterious property. So in confined phase, so theta angle periodicity is realized quite non-trivial. So this is monopole condensation. This was dione condensation. And there was some non-trivial transition at theta equal 2 pi, theta equal pi there. And our motivation to understand, to introduce GN1 form symmetry is to understand this kind of dynamical phenomena. And from the viewpoint of symmetry, using the recent power of symmetry. And let me go back to this problem.
They are related to the previous section about the pi n here.
Mm-hmm.
If we around the function background, then I think the spectrum wouldn't be quite periodic before.
Right. Exactly. Yeah, that's one way to understand it. Exactly. Yeah, yes, right.
Need to have 2 pi n periodicity, Newtonian, but if we around the background gauge, then even the 2 pi periodicity is broken.
In a sense, yes, and that can be seen from Lagrangian viewpoint from now. Or since that Chern-Simons operator is anomalous under one form symmetry, so yeah, that unitary operation that realizing this 0 and 2 pi is very subtle under one form symmetry. Yeah, that's really the point. That's the point.
One of you probably can you summarize what you said? Or in terms of pi periodicity, what is not correct statement? Because there's been
but that I'm going to explain from now. Yeah. So let me introduce the background gauge field for one form symmetry. So yeah. Yeah. Yeah, here I just formally write down the coupling between gauge field and B, but what is really done is, in the case of lattice discretization, what we are doing is just this kind of GN rotation coupling constant. And this is a topological term coupling to B. And previously, so when we set B is 0, so we say Q topological is quantized to integer, and we call instant number. But for example, classic result by Van Baal in 82 or 3 said that if you introduce this B field, at that time, this B field was called what is called 't Hooft twisted boundary condition. It turns out that this is shifted by so this is some topological But so important thing is, so yeah, let's partly forget about this bit formula, but this is 1 over n fractional shift of integer. So originally topological charge was just a usual instanton number. But if you introduce non-trivial B field, so this topological charge is no longer has to be integer quantized, but that can be shifted by 1 over n. Yeah, and this one can be written as, let's say, b b of let's say let's consider, yeah, for example, if we take for the case of torus, so let's say let's take mu and nu direction and integrate this b, and let me call this as n mu nu. This is z over n in modulo n. Then this one over b cup b turns out to be 8 over nu. And what is really called a first twist is this one. So this is turns out or first flux. And using this first flux, you get this quantity. And by looking at this symmetry of exchanging mu, nu, rho, sigma, etc., this turns out to be integer, and fractional shift of topological charge is given by 1 over n times this integer quantity, and you have to still sum up all integer instanton number.
That expression, if it is not pure manifold, it is a 1 over 16 instead of 1 over 8.
This is always, I think, 1 over a.
I thought that the half of the copy is either only on the spin manifold, we should be half.
Okay, I see. Let's see.
But if that's not for sure.
Yeah. So in the case of a non-spin manifold, I think you have to make that one as n minus 1. Yeah.
Yeah, it's n minus 1 over 2n.
Yeah.
Right.
Yeah,
n minus 1 over n.
Yeah. Right. Yeah. And here, yeah, I'm implicitly assuming spin manifold, so that n minus 1 part, it can be basically equivalent to minus 1 over n because of that assuming of spin manifold. Yeah, okay. Yeah. And let me now then compute partition function at theta equal to pi, and whether this is turns out to be same with how it is related to the partition function of theta. Then non-trivial part of having this extra 2 pi is this one. But then, yeah. And we get 2 pi I QB. But QB is up to this integer. So this integer part non-trivially depends on this dynamical gauge field. But that part drops because of 2 pi I times integer part. So you can replace this QB as minus 1 over n. What's b squared? And now this part becomes independent of this dynamical field A. So you can bring everything in front. Then rest is the same as the usual partition function. So you get minus. Yeah, right. Right. So now you get extra phase in front of the partition function. Oh, yeah. So now since we are having this one, so yeah, so because of this appearance of this phase factor, so basically, so now this nicely explains why this phase, so why you should have a phase transition at theta equal pi. Because if you compute partition function for this monopole condensation, with background gauge field B, let's say this is normalized to just 1. But if, for example, this dion condensation case, if this background gauge field dependence is given by e to the minus 2 pi I over n, yeah, 1 over 2 b up b, then monopole condensation and dion condensation have a different type of response to the background gauge field by this amount. But then this kind of relation for the partition function with the background gauge field is satisfied. So interpretation of this abelianized picture from the viewpoint of symmetry is monopole condensation is really trivially respond to background gauge field for the one-form symmetry. But dion condensation has a non-trivial response to background gauge field for the one-form symmetry.
Why if you normalize monopole partition, why diode should have that SPP?
Basically because we here assume that theta equal 2 pi phase is realized by dion condensation. Yeah. And since the partition function at theta equal 2 pi and theta are related by this quantity, yeah, so yeah, dion condensation on this point should be determined by monopole condensation partition function, like from this relation, and you get this kind of different. Yeah, right. Yeah, so here I'm assuming this one. So relative to this monopole, dion should have extra this phase. So that is more correct statement. Yeah. So obviously I do not have a time to explain semiclassics, but but let me give a very brief explanation about semiclassics. So here, so what I have done is first assuming a monopole or dual superconductor picture and explain confinement. And now theta angle has a very non-trivial realization in the confinement vacuum, and we are having non-trivial dione tower, and those condensations are crucial to have 2-pi periodicity. And we explain, we give a reinterpretation of this interesting phenomenon from the viewpoint of generalized symmetry. And now idea is from using this kind of knowledge of generalized symmetry, so can we give more concrete semi-classical computation to explain this kind of phenomena? So that is what Meet-Hart and my collaborator Yue Hayashi are heavily working on this kind of subject. And the point is, so Yang-Mills on R4 is very strongly coupled. And of course, this means it's difficult to analyze. So if we can gain some of the information rigorously out of symmetry, but to get a concrete realization of, for example, monopole condensation analytically, it's quite hard, tough subjects. So idea is, while keeping property of confinement, so we want to make deform theory to be weakly coupled. And studying this weakly coupled side of the theory, so we want to learn something about confinement. That is the idea of this kind of semi-classical explanation. And this kind of weak coupling deformation of this strongly coupled confinement phenomena has a very long history, like supersymmetric Yang-Mills or R3 cross S1 semiclassics. But what we are recently proposing is put Yang-Mills theory on R2 times T2. And on this T2, we turn on this background gauge field N over P. And this P, so P, top-of twist with 1. So as a concrete example, you can take this P to be just 1. And in this, so in this setup, so because of this existence of magnetic flux, so this kind of non-trivial relation between partition function at theta plus 2 pi and theta are kept intact even after small t2 reduction, or even after getting two-dimensional effective theory. Thanks to this background gauge field, you can preserve this non-trivial relation under this T2 compactified setup. And because of this first twist, we can say that so GN1 form. So GN1 form symmetry in 4D in R2 times T2 setup. So this splits into GN1 form times 2 zero form symmetry acting on Polyakov loop along 3 and 4th direction. So this is yes. And it turns out that so this part is classically unbroken. Thanks to the first twisted partition to first twisted boundary condition. So if we just consider small teeth compactification without introducing the first twist, that is basically considering the high temperature Yang-Mills theory. And we know that if you heat up Yang-Mills theory, so you get the deconfinement phase transition. But in this case, because of this non-trivial to first twisted boundary condition, prefers center symmetric vacuum. So that kind of even if you heat up the system with this twisted boundary condition, you do not encounter deconfinement phase transition. And in this case, so interesting thing is if you consider 4D instanton, so if you consider 4D instanton, then on R2 times T2 with this kind of twist, so you get the effective two-dimensional system. And this 4D instanton splits into n constituent. And this one is really nothing but what people call center vortex. And summing basically this center vortex causes a confinement. Confinement of Wilson loops. So what I wanted to emphasize is this first twisted boundary condition is basically the background gauge field for the one-form symmetry. And this one-form non-trivial background of one-form symmetry splits for the instanton into n constituent of center vortex. And since this constituent of center vortex has magnetic flux 1/n and topological charge also 1/n.
The winding charge.
This is really topological charge of 4D instanton. Instanton topological charge is 1/n.
Are we talking about just winding of that measures of the vortex itself? That's the one of the thing.
Yeah, so it turns out to be equivalent. So in that sense, yeah, you can regard that way. Yeah, yeah.
When you say that center-vortex is underlying component of Wilson loops, what that must be what? Like they trigger condensation of center charge or what?
Oh, yeah, so let's say this is R2, and let me introduce Wilson loop here. And if center vortex goes in this way, then this Wilson loop gets a GN phase. Oh, Wilson loop. So this center vortex rotates the phase of the Wilson loop by this amount. So, and in that sense, so this is a 2D vortex-like configuration that rotates the Wilson loop by center elements. So that is why we call it center vortex. And then, so partition function in this setup can be considered as a gas, summing up a gas of center vortex. So basically just considering the ground canonical partition function of the gas of center vortex, you can compute partition function of Yang-Mills theory in this setup. And let's say n bar is a number of vortex, anti-vortex. And since total, yeah, and so you get n factorial, n bar factorial, s vortex. So this grand canonical partition function of the gas of center vortex and anti-vortex system, it can be basically written in this way. But there is an important constraint that since total topological charge, each carried by vortex or anti-vortex is just 1 over n. But you want to say that so topological charge on R2 times T2 is just integer quantized. So you want to say that n minus n bar wants to be 0 mod n. And that delta function constraint can be written from this way. Into the 2 pi. N times k. So you can write this way. And so it turns out that, so this turns out to be 0 n minus 1 e to the minus. Yeah. Yeah. So basically, so this is a ground state energy for branch K as a function of theta. And if you draw energy as a function of theta, then you will get, say, this is 2 pi. And yeah. Yeah, something like that. So this is K equal 0 branch, K equal 1 branch, K equal 2 branch. And you can explain say transition at theta equal pi. And this K really labels K in front of this B coupling. So basically, although everything is computed semi-classically, but we can nicely reproduce the non-trivial theta dependence of the Yang-Mills partition function by considering on R2 times T2. And what is good is in this R2 times T2 setup, everything can be computed analytically. So although this kind of knowledge assumes monopole condensation, which is a strongly coupled phenomena, but in this R2 times T2 case, so gained by intuition from symmetry, generalized symmetry, we can nicely reproduce everything for dynamics of Yang-Mills theory. And I couldn't talk about it at all, but even if you consider fundamental quarks, you can basically do similar kind of computation. And in that case, we can learn about the physics of the eta prime particle, which is related to U1 axial problem of QCD. Okay, so since time is up, so let me stop here and thank you very much for your attention.